All right, so today, so we'll continue the MOS working, but I'll again repeat a lot of the stuff we've done. It'll be more, a little bit of a more info graphics kind of a presentation where since a lot of the things I've covered, I'll just repeat it, but I'll go much faster. But do stop me anywhere you have a question. So basically what I'll do is I'll cover all the background stuff. We'll just do the, look at the PN junction again, the equation for current, and then we'll just look at the MOS threshold voltage part of it, okay? And then once we're done with the threshold part, we'll go into the current equation. We'll see, how far we get today. All right, so the first part, I'll just quickly go through the semiconductor part. Again, this will be a repeat, but still pay attention. So we started with the semiconductor, and the band diagram basically, like we said before, it essentially presents the electron energy. So all it tells you is, just give me a second here. Yeah, so it just tells you the energy of the electron, and there are two bands which tells you if it is a conduction or insulator or not. The valence band, if your electrons are having energy below this band, then obviously they'll not conduct. If their electrons are in this above this conduction band, then they will conduct. So for example, for metals, they're all here. For insulator, they're all here. For semiconductors, some are here. For example, at room temperature, some of these electrons will break free. They'll jump into conduction band, will leave a hole behind, which is a positive carrier. So if your positive carrier is below the valence band, they will conduct. If your negative carrier is in the conduction band, they will carry. Fermi potential. So band gap, the band diagrams, if you're not grasping it completely, that's fine. Really, honestly, all you need it is to find out what happens during contacts of different types of materials. That's where really the band gap helps you a little bit. If you just say, okay, this is the result of the band gap, that's all you understand, that's fine. Because we are not designing devices, we are understanding devices. So you can perfectly understand without going deep into the band diagrams. But it essentially gives you an idea, especially when you put two different materials together, okay? So another concept in the band diagram which helps you analyze devices is called the Fermi level. And the Fermi level basically tells you what's the probability of an electron occupying that state if it is 50%. 50% probability of an electron occupying that state. So you can see, for example, if you have an intrinsic in the sense like a pure crystalline silicon, which has perfect bonding. Each silicon is bonded by 4 on the side. Then it's halfway in between, because every time an electron breaks, it leaves a hole behind. So the energy is kind of halfway in between. In an intrinsic semiconductor at room temperature, your carrier concentration, that is the number of free electrons available in a intrinsic per cubic centimeter, is about 1.45 into 10 to the power 10. You don't have to remember the number, but just in case you think, oh, that's a lot of electrons, it's conductive. But if you take into account the number of silicon atoms, which is 5 into 10 to the power 20, so you're actually having only one carrier per 10 to the power 12 atoms. So in other words, at room temperature, just a crystalline silicon is not very, very conductive at all. It's in fact very resistive, okay? And these two helps you understand some of the semiconductor stuff is your electron concentration is at room temperature is whatever is the intrinsic concentration, that is 1.45 into 10 to the power 10. Your whole concentration is also the same in intrinsic, because each time electron leaves behind a hole. And then there's a semiconductor law, which is called the mass action law. If you take the product of the holes and the electrons, they are the product of the intrinsic concentration. Again, this helps you find out majority and minority carrier of doped silicon, which I'll show next. So that's intrinsic. Now, if you want to make it conductive, what you do is you dope the silicon with some impurity. For example, let's say we did this with phosphorus. So we put some phosphorus inside it. Then what happens if you look at the band diagram, the Fermi level of that particular material goes closer to, because now there is an extra electron. Depending on how many dopants I have doped per cubic centimeter, this will get that much closer to the conduction band. And because the Fermi level is very close, the number of electrons available at room temperature is quite a bit for conduction. So you have quite a few um, um, electrons for conduction. And one quantity we use a lot when we're doing device analysis is called the Fermi potential. It's essentially the difference between the intrinsic Fermi level and the new Fermi level after you have doped it, which is given by this expression, kT over Q, natural log of the intrinsic semiconductor over the dopant concentration. And in VLSI, this is a good number to always remember. This is called the thermal voltage. kT over Q at room temperature is about 25 millivolts. Actually, it's around 26, but remember it as 25 millivolts. You'll be using it a lot, so knowing that number actually helps. And the ND is your donor concentration. So number of donors per centimeter cube is your donor concentration. Okay. Now, when you're doping it, obviously on one side is your concentration of intrinsic semiconductor, which is 10 to the power 10, typically 1.45, but I'm just saying roughly 10 to the power 10. And then the number of atoms available, silicon atoms, is 10 to the power 22. So obviously you want to be somewhere in between. You can't obviously go above this. And you obviously want to be higher than this because this is very resistive. So the dopant concentration, you want to make sure it's much higher than the intrinsic level, but much lower than the number of atoms available. So typically you'll see they're within 10 to the power 15 to the 10 to the power 18. If you go higher than this, then the material actually becomes what's called a degenerate. It's no more a semiconductor. You can't use any of the formulas or techniques you're using before. And typically, like for example, in a N material, it'll be called as N plus. And if it is around 10 to the power 15, it's just called plain N or N minus. So basically, you'll hear a lot in VLSI, oh, this is heavily doped N, this is lightly doped N. It's basically telling you that where the dopant levels are within this range. If it is close to 10 to the power 15, it's called lightly doped. If it is close to 10 to the power 18, then it's heavily doped. Okay, and the Fermi potential, if it is doped around 10 to the power 18, is about 0.45 volts. If it is around 10 to the power 15, it's about 0.28 volts. Don't have to remember the numbers, but good to know these numbers because you can quickly calculate built-in potentials and stuff like that. Okay. I think somebody is not muted. If you can mute yourself, let me just check. Yeah, I think Himadri and it's probably Sanjit sir. Yeah, if you can mute yourself. If you have some questions, obviously go ahead, but if not, just. Okay, and so that's how you do N type. For P type, obviously, and oh, the last thing I wanted to say is that once you dope it, the electron concentration is pretty close to the dopant concentration. So for example, let's say you have doped it with 10 to the power 18 phosphorus atoms per centimeter cube, then that's how much electrons you're going to get at room temperature, pretty close to that. And if you use that mass action law, which I showed you in the previous slide, you can calculate the holes. You can see the holes are only about 200. So your electrons are like 10 to the power 18, and these are only 200. So those, in semiconductor language, this is called majority carriers. In N type, this is called the minority carriers. For the P type, it's exactly the opposite. You find a dopant which has one less electron in the valence band, so basically gives you a hole. And if you dope it, then your Fermi level actually goes closer to the valence band, because for holes you need to be in the valence band. And the Fermi potential, again, the same thing, except this order is reversed. And again, the same principle here. When you dope it, you want to be much higher than the intrinsic concentration, but much lower than the number of silicon atoms in that particular crystal. And after you dope it, the whole concentration is pretty close to the number of dopants. And let's say you've doped it with 10 to the power 15. That will be number of holes you'll get. Then again, if you use the mass action law, your number of electrons, you can see now they're much more because your number of holes are less. But still, almost 10 orders of magnitude less than the holes. So these are still the majority carriers, then these are still the minority carriers. Okay. All right. So now if you take these two materials, join them. So for example, let's say take a p-type, which is heavily doped, so about 10 to the power 18 per centimeter cube acceptor atoms like boron, for example. Then you have an n-type, just a plain n-type. So let's say it's lightly doped, then it's about 10 to the power 15 phosphorus atoms, let's say. And when you take two of these semiconductor materials whose electron energies are different, and you join them, for example, in the n-type, the electron energy is higher than the p-type. So what will happen is they'll start moving from this direction to this direction. But as they're moving, they keep leaving these immobile ions, positive ions behind, which will create an electric field between this end to that end, and it'll keep happening this till this electric field can fight back the potential difference which exists between a plane P plus and N plus. If you look from a band gap, a band diagram perspective, um, the, the law of thermodynamics says that the Fermi level, which is the probability of electron, the energy of a 50% probability of electron, the energy state, that should be same throughout the material, and makes sense because if it is not same, then there'll be current. But obviously this is there's no electric field here, so there shouldn't be any current. I mean, no applied electric field. So the Fermi level should be the same. Now the thing is that if it is same, the p side still should look like p side, where the Fermi level is closer to the valence band. The n side should look like an n-type, where the Fermi level is close to the conduction band, because these materials haven't changed anything. They're still like before. Only this part has changed, which means that this band has to connect. And that's the band bending you hear about when you do a connect the materials. And that's what I was saying, that where the band diagrams really help you is understanding when they come into contact. And the amount of this bending which is done is basically the difference between the two Fermi potentials, or since they're one term is negative, it's really the magnitude of the two Fermi potentials. That's the potential difference which is built in between these two p and n junction. Okay. And if you look at the charge, obviously you get a positive charge in this whole depletion area, which is Q times the dopant density. That's because that's your density level of your dopant atom. So if they're leaving behind the positive atom, the concentration also remains the same, which means that if I take the area under this curve, then that's the total charge in this n-type area. And if I do the same thing on the p side, that total area of this charge curve as a function of distance gives me the total charge enclosed in this particular depletion area. And if I look at the electric field, obviously the electric field here is 0, then it starts going up. The peak is here, and then as each electric field is ending in each one of the negative ions, it ends to 0 and goes back here over. And the peak is actually in between here. The reason this is important to understand is because when we do threshold voltage, we want to see what is this depletion width and how much charge I need to provide in this depletion. In order to calculate the depletion charge, we first need to calculate what the distance is. So this is a little bit of involved calculation. So what I'll do is I'll just show you the concept, how it is calculated. Then you can maybe go back to the books, or we can just take if you absolutely have some doubt, we can take some questions now. So what you do is you basically, if you take these two blocks here, so I've just kind of taken out these two depletion areas. And if I want to find the charge in this or this, which is same, right? They're just opposite magnitude. Then I can apply what's called the Gauss's law, which is actually one of the Maxwell's equation too. It's a fancy term, but essentially what it is it just tells you that if I enclose this entire volume, and if I calculate all the electric field lines coming out, it should be equal to the total charge divided by the permittivity of this material inside. Okay, so that is essentially saying that this electric field at the peak here is either all the charge in this divided by this permittivity, or all the charge inside this divided by the permittivity. And that gives you the relation between the charge density and the peak electric field. And the reason we use that is because we want we can find a relation between this potential difference and the peak electric field using what's called a Poisson's equation. Again, it's a fancy term, but it's basically if you have charge in some. So, for example, you remember in a dielectric, we said that electric field is constant. That's because there's no charge inside it. If there was charge inside it, you would use this to find out how the electric field and the potential is varying. And that's basically this equation right here. It's basically the gradient or the second derivative of the potential with respect to x is the charge divided by the epsilon. It's based on the Gauss's law. But again, the reason we are telling this is we're trying to find out what is the amount of charge which is enclosed in this. That's what we are doing all these experiments for. All this analysis for. And the way we are trying to do that is trying to figure out after this depletion stops, what is the length? And I know the charge density because I know what dopant concentration is. I'll just multiply that with this and I know the total charge. Okay, and that will be useful when we do the threshold voltage calculation. That's why I'm showing you this. Again, if you don't follow all this, just know the final value for it. So if I substitute these two equations into the Poisson equation, what you get is this total difference in the potential is equal to this quantity here. And if I take this particular expression, which says that the dopant times the length of XP is equal to this, that's again comes from because the charges are the same, because it should be charge neutral. This whole thing should be charge neutral here. So if that's the case, you do all that, you actually find the length of the depletion in the P area, you find the length of the depletion in N area, and I can do one approximation, which is called a one-sided junction. One-sided junction means you're assuming that the P side is so heavily doped that this is almost like a sheet here. So all your depletion area is on the lowly doped side. If you make that approximation, this Na over Nd term becomes 1. Then you have this expression here, and you multiply that with Nd, you get the total charge inside it. That's why we did all this stunt, okay? So just remember this expression here. Inside a depletion, your charge enclosed is 2q epsilon s times the dopant concentration times the potential difference within that semiconductor between the two walls of the depletion area, like for example, between these two walls, or in this case, these two walls here, okay? So is it at least vaguely clear so far? Any questions? You can raise your hand if you have any questions, or like as I said, I'm showing you all the steps so that, because I always get a question, so how did you get this? So a lot of times I said, yeah, just, forget it, read on your own, or just believe me. But here I just try to give you few of those steps. But was that okay? Or somebody, do you want me to repeat any of this stuff? You can raise your hand. Okay, Chirag, go ahead. Do you want me to just repeat it, or which part? Is there something you didn't
No,
understand?
sir. Why are we using that Poisson's equation?
Oh, the Poisson equation is if I want to find out the relation between the electric field and charge, electric field and potential in this region, then I have to use that equation because there is charge inside it. So for example, in a capacitor, if I have just two plates, like this were two plates, then I don't need Poisson's equation because I know dV over dx is equal to E. E is constant. But there is charge here. So you actually have to use the Poisson's equation, basically, which is telling you the gradient of the potential is equal to the charge enclosed in that. Okay. So it's basically trying to find out a relationship between electric field and potential if you have charge inside it, and which is the case here. Did that make sense?
Yes, sir.
Okay. Like I said, our ultimate goal was to find out the total charge here. So the idea was if I know how much distance is this depletion width, I know my concentration, the ND, Q times that will give me the total charge. So that's the total charge inside a depletion area. That's one of the VT terms. If you remember last time, I just said depletion charge over Cox, but I didn't give you the expression for it. But every book you open your VT expression, you're going to see this. So I just wanted to give you the background for it. Like where is this coming from? Okay. All right. So I'm hoping at least, making 10% sense at least. So I mean, hoping 100%, but hopefully a little bit. Okay, so the next thing I want to cover is, so this is all I want to cover from a PN junction side of the story before doing the threshold voltage stuff. The next two things, which again I had covered last time, is I want to quickly show you the, uh, oh, actually just show you the forward. Yeah, so just quickly give you an expression for forward and reverse bias. Now, forward bias, I'm not going to go into the equation of it. In CMOS, we really never use the diode in forward bias. That's something we obviously always try to avoid it. But if you take a PN junction and obviously apply a positive potential with respect to the negative, and you keep increasing that voltage, that's essentially your IV characteristics. So essentially what you're doing is you're first trying to fight this potential, and after that you get what's called a charge carrier concentration at the edges, and then because of both drift and diffusion mechanism, you get a current through the diode, which has an exponential relationship with the voltage across it. And this is approximately, obviously, because it's 1 minus of this. And then the reverse bias, the current is almost zero till you get a voltage where it breaks down. So breaks down in the sense, there's what the phenomena called avalanche, which basically just destroys this junction, and then you almost get like a short, basically. Okay. And these are some of the expressions for IS and the phi naught, which we just talked about, but that's something I think you can refer to. The books will not go deep into it. The PN junction, which is important to us from a VLSI perspective, is the reverse bias junction. You have like millions of, you have 10 million transistors, you have 20 million reverse bias junctions. So uh, that's worth spending time understanding what it is. I think we've already talked about it few times. I'll again give you an idea on what happens during reverse junction. So you put a P and N, then you have this built-in potential. Now, instead of putting a positive potential P with respect to N, now you do the opposite. You put a positive with respect to N, which is in series with this built-in potential, because the built-in potential already had a positive potential here. So it's just adding on top of that. So as you add a little bit more voltage to it, it just add a little bit more charge to it, same charge on the other direction. Okay, and so essentially what it looks like is a capacitor, because you added this extra delta V here, it added a delta Q, and the length changed at delta X in time. In a normal capacitor, the length, obviously, if you have a dielectric, the two sides of the dielectrics are same. You just get delta Q and you calculate C, which is equal to delta Q over delta V. In this case, your length is also changing. So essentially what you're trying to find out is your this nonlinear capacitance. If you look at it as a differential capacitor, that means or an incremental capacitor, in the sense you give a certain reverse bias voltage and you change a tiny amount of the voltage and you see a tiny amount of charge go into the node. That basically tells you what the cap is. Um, so what I did here was did just a kind of an algebra stunt where I said, okay, I want to find out delta Q over delta V, which is the same as delta Q over delta Xn times delta Xn over delta V, because these two will cancel. Or in a differential form, you can write this as the derivative of Q with respect to Xn and derivative of Xn with respect to dV. Um, and if I use that previous formula for my length and differentiate it with respect to VR, that's what you're going to get. And you substitute back in this equation, and you basically get the entire CJ naught equation. And if you, your entire junction capacitance as a function of your reverse bias voltage, which I had given you the expression before, where it was some CJ naught times phi naught plus VR. And you can see as your VR is increasing, your capacitor is decreasing. And the reason for that is because your distance is increasing. So, in a normal capacitor, it's epsilon over Tox. So essentially your Tox is increasing. So that's why your capacitor is decreasing. And this CJ naught quantity is basically this quantity, which was calculated from this, doing the derivative of this Xn with respect to TQ over TXN. So just showing you the math behind it, how we got to this formula. You don't absolutely have to just go through it right now. Just understand the principle. Basically, the way we are calculating our capacitance is just like we do the normal capacitance, but the difference here is because the length is changing, I need to capture that. So for example, here I'm trying to find out the delta Q over delta V, but the delta Q actually depends on delta Xn as well. So I kind of split this equation into two of these forms, and using that previous equation for depletion length and charge, I do a derivative of that Xn with respect to VR, and then get this expression, which I substituted here to get the final expression. And I think in my first lecture, I gave this as 1 plus VR over phi naught, which means that this phi naught is included in CJ naught. So, um, depending on which book or literature you read, it might be in different forms. So just be aware. So if you see somewhere it's written 1 plus VR over phi naught, that means it's the phi naught is actually included in this CJ naught. If it is not, then it's just this quantity here. Okay. Any questions on this one? Like I said, I kind of qualitatively explained last time. So this time I just wanted to give you, so when you see a book, the expression for CJ, if you're wondering where this came from, that's how it came from. Basically, you're trying to find out the delta Q over delta V as a function of this length as it is changing. Did that make sense? Any questions on this one so far? Okay, so looks like everyone's fine with this. Okay, so the last thing on the semiconductor part I wanted to talk about is contact potential. Again, this will be something I'll talk during the threshold voltage derivation. And I kind of mentioned that last time, so I'll show that again. So the contact potential is if you take any two materials, like it could be metal semiconductor or metal insulator or any materials, do it. Then because of this contact, it's almost like the built-in voltage of the PN junction, but here it's talking about any material basically. So if you take two materials, M1, M2, and join them, you're going to get this potential difference because of the electron potential difference, like in the PN junction, right? So if I plot the potential of the electron across this junction here, or contact here in this case, it'll look like this. It'll have some potential of the electron in M1 and it'll drop to M2. And this difference is what's called the work function difference. And the reason it's called work function difference is this potential difference is nothing but if you actually took an electron from this material's Fermi level to the vacuum level. So basically, if I pluck one electron from this material and take it to some part of the galaxy where there is no charge at all, I'm going to spend this amount of energy, which is this called the work function of this particular material M1. This material M2 has the lower Fermi level, so I'll do more work. So the work function is to take an electron from here to some point in galaxy where there is no charge. It'll cost me this much amount of energy, phi Wm2. When I join them, it's basically the difference between these two work functions. So it's almost like I'm taking an electron from here to infinity and back to this material, and that's nothing but this potential difference. Okay. And the other thing I showed you last time is, so this is two material. Now, the interesting thing is that if I take a stack of materials, so I take some n materials, I start with M1, some material M2, M3, M4, M6, 7, 8, 9, n minus 1, and Mn, right? If I stack them up and theoretically look at the potential here between these 2 points, then the contact potential or this potential difference is actually the work function difference between these last two materials. It doesn't matter what material is in between them. So if I take these M2, M3s, take two materials away or swap them or add another material or do whatever inside this, the contact potential still remains the same. Okay. If you remember, I asked a question last time that in a PN junction, if I put a voltmeter, so for example, in this PN junction, if I put a voltmeter, will I be able to measure the built-in potential? So I think some of you said yes, some of you said no. Now, with this picture in mind, can somebody tell me if you can measure? So for example, now um, if I take, so let me ask the question again. Can't get the pen. Just 1 second. Okay, so the question I asked is, you have a PN junction, right? And then obviously you got this minus, and this is, let's say, about 0.7 volts. So my question was, if I add a voltmeter here, will I see 0.7 volts here? So using this particular phenomena, can somebody tell me yes or no?
So we could see.
You will see? Okay. Yes,
No,
okay.
sir.
No? Who said no?
So,
Rachita? Rachita?
No,
So,
sir, because
Shatabdi.
We cannot.
okay, so maybe let me ask, who said no? Raise your hand. A lot of people said.
me, Smritireka.
Okay, so why no, Smritika?
Because when we connect the potentiometer,
Yeah,
the two set contact potential will form, and they will um, uh, plus minus they will each other, and ultimately it will become zero.
okay. I think, yeah, I think I understand. So basically what Smritika is saying is that the way when I put the voltmeter, I'm essentially adding a metal, right? So this probe is nothing but a metal, and that metal has to do a contact here. And I have to put another metal here, and that metal also has to make a contact. So let's say both the metals were M1 and M1. Then according to this phenomena here, contact potential, then this will measure the contact potential, which is phi M1 minus phi M1, which is equal to 0, right? So that's why you'll not measure this. So if you just take a diode and put this, that's because the contact potentials will cancel and you're just going to measure the contact potential of the two metals. So obviously when you put it inside a semiconductor device, you're not, that's why you don't do M1, M1. You have to always dope it with some P plus or N plus before you actually make a contact. That's one of the reasons you do that. Okay, makes sense? Any questions on that? Okay, Prajita, go ahead. What's the question?
Those are the answer. She said the answer.
Okay, good, no problem. All right, so that's the last thing. Again, this is something again I'll show you in the VT calculations. So let's see, two people. Okay, anyone has questions? You can just unmute and ask right now.
Sir, I have one question.
Yep. Okay, go
So,
ahead, Puneet. Yeah.
so basically, the phi contact which you're talking about, this is not the built-in potential.
It is actually kind of built-in potential. So what will happen is if you just did, like, for example, a PN, 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 and then there'll be built-in potentials of all the PN junctions in between, and finally what you get is the potentials on the two end. So it's sort of like the built-in potential, but this is more when you're doing contacts at both the ends or you have multiple stacks. So honestly speaking, I don't know why they differentiate it. They should call it the built-in potential. I honestly don't understand, because if you look at the built-in potential, it's also sort of phi p minus phi n if you calculate it, because that's also the work function difference.
So the point is like
Yeah,
in the design when we have this poly, then the contact, and then
right,
the metal, then the via, all that stack is there.
right,
So there is a one thing is like in a potential drop. So that
right,
potential drop is because of the resistance, whatever the resistance we have.
right.
So, but this potential is also supposed to play a role in that voltage drop. Am I right?
Correct, because like, for example, you take a diode, right? So if you take a diode and you forward bias it, this potential plays a role, because that forward bias is not going to give you a current right away, right? You have to fight that potential for some time. Same thing when you do, like, for example, a MOS oxide semiconductor sandwich. When you calculate the VT, if you don't take this into account, your VT will be like 0.25. But you take this into account, suddenly this is minus 0.65, because that comes into potential. So yeah, it is built into all these semiconductor devices, and they play a role, all these built-in potentials. And that's why you'll see that when you're putting a metal on a semiconductor, you have to always have a P plus. Otherwise, what will happen is you'll form a Schottky junction otherwise. For example, if you have a P minus and you want to put a contact on it, then you have to do a P plus first, then put a contact um, before you bring it out to some connection.
So,
I,
so the follow up, like you were saying, like if we have M1, M2, M3, and same M1,
yeah.
so this is equivalent to if I have M1 and Mn directly.
Yes, exactly. So let's say you just take this and you just take this and cut it off. It's still M1, M2. Or if you have M1, M2, Mn, then yeah, still M1, M2. So the contact potential, or the sort of the built-in potential difference between them still remains the same. I think the reason it's called contact potential is you start worrying about it when you start making contact to uh, put it in another device, whereas the built-in is you just make a junction and it's a built-in voltage. So I guess that's honestly speaking, nobody ever explains why they name
Okay.
it differently.
Yeah. So I was just thinking from the design point of view, like we have the metal stack, and
Yeah,
there we have from poly to M7, M8, M9, M10.
right, right.
So from this theory, it looks to me like from it doesn't matter. Means built-in potential is not going to change a lot, or you can say the drop. If I know, like, okay, what is the maximum potential difference? Like, let us suppose the M10 versus the poly.
Uh-huh.
Whatever with the built-in potential, like
Right.
whatever the phi contact or thing, that's going to my maximum value, because
Correct.
irrespective of whatever with the level I'm going to use.
Yeah, I think, yeah, correct. Like, for example, in a MOS, you have the poly,
Yeah.
uh, and then you have oxide, right? You have the oxide, and then you have the semiconductor, right? So when you apply a voltage across this, all you're fighting against is phi poly and semi, phi MS, let's say, call it.
Okay.
These two. This potential difference, this work function difference, you don't care, because ultimately it'll be between these two. So that's what first you have to put, that flat band voltage. You have to work against these two potential or the work function difference. And let's say here I had an oxide and some other material here, like some gallium nitride or something. It's still 5 ms. Or I have another material P plus something, still 5 ms. So that potential I have to fight to apply any current through it is still the same. And obviously, this structure will do something different for other things, but that built-in potential will be this 5 ms for that.
Okay, so from the capacitance point of view, yes, sorry, yeah, so that is going to be like my next question. Like
Yeah,
this built-in potential, because of this built-in potential, there is a capacitance.
right,
And now if you're saying like if between M1, M2, M3, M4 till Mn,
right.
like if the capacitance is with respect to the M1 and Mn, so like here you have explained poly, oxide, and semiconductor.
Right.
So, so from the capacitance point of view, it is same if I will just connect poly and a semiconductor.
Correct. So I think if I understand correct, so if I draw this again, so you have poly and you have the oxide, right? And you have the semiconductor. So if you want to see the effect of this capacitance, this oxide capacitance, you have to first kind of undo this potential, this 5 ms, and then you'll see this capacitance after that. Is that what you're saying?
Yeah. So what I was
So
just
for,
trying to
yeah,
understand, like in the like oxide is going to work as a dielectric constant in this
right,
particular case. So if
right,
so, usually what happen, like we usually we usually add a multiple layers of dielectric just to reduce the dielectric constant,
right,
effective dielectric constant, and that
right,
changes over the capacitance. But
right.
from this theory, it looks to me that even if I will change the dielectric constant, that's not going to
No, no,
affect
no.
my.
No. I think the capacitance still changes. So for example, let's say this capacitance was some value Cox, right? Cox. All this is saying is that, by the way, if I had just two metal plates, I applied V, some voltage V, then let's say this was C, then my Q is equal to CV, right? And what this is saying is that, oh, by the way, first you have to make your V equals to phi ms. So let's say that was 0.1 volt, I mean 0.5 volt. First you have to apply 0.5 volt. After that, you'll see the oxide capacitance, which is Cox times the area times the V minus 0.5, just like the threshold voltage. I think that's what it is saying.
Oh, okay. So
You
you are
got it,
saying
right?
we are not going to apply the this equation Q equals to CV directly until and
Exactly.
unless
You have overcome this value.
overcome
And if
this.
this was poly, then you don't have to overcome anything, because then this value is 0, then you get right away. All the charges happen right away. It's only when there are two different type of material, you have to come to that difference. If this is metal, you don't have to do anything. If this is P plus, this is P plus, you don't have to do anything. If this is N plus, this is N plus, you don't have to do anything. You see the point, right? So the
Yeah.
capacitance appears after you put that contact potential.
Okay. Yeah. So I become confused with this thing. So I was like, this built-in potential is directly related to the capacitance.
No,
Now
no, no,
that
no. The
means
capacitance still appears as it is, just that because you have two different materials, if you just had two metal or P plus or two N plus or anything, then you'd see the capacitance right away. Whereas if you have some different material, you have to first overcome that work function before you can have electric field in that capacitance come through.
oh,
I
got it,
think that's
got
all
it.
it says.
Thank you,
Yeah.
sir.
Okay. I hope that. All right. I hope that is kind of clear right now. All right. Any other questions from the students? Okay, so the two other things before I show the threshold voltage is I think I showed you this electric field and potential inside a capacitor. Again, we do that a lot when we were looking at, so I thought this would be good to just review that. We went through this last time. So if you just have a plain capacitor where you have two metal plates and a dielectric in between, you apply a voltage, and let's say the distance between these two plates was Tox, then the electric field is constant. So here you can just apply Gauss's law. So Chirag's answering your question, if I want to find out the relation between E and V, because there is no charge inside this, I can just apply Gauss's law to give me this slope between V and E. And the capacitance is just given by the relative permittivity. This is the relative permittivity. This is the absolute permittivity. The product of that divided by the distance, right? So that's your what's called your linear cap. So linear cap in the sense your Tox is not varying with your applied voltage like it was varying with case of diode. So this is just a simple cap, but I just wanted to show you that inside the cap, the electric field is constant because there are no charges. And since the electric field is a derivative of the potential, negative derivative of the potential, then the potential varies linearly from this plate to this plate. Okay. And the last thing I wanted to cover is the current conduction in semiconductor or any resistive material. So I've taken a block here which has length L, W, and a height H. And let's say this was a semiconductor material, doped with some dopant, N-type dopant, heavily doped. So when I apply a voltage, I want to find out the current through it. So first thing I do is I find out what the potential through it is. And you can obviously use all the previous theory, but a simple way to look at it is because this is a uniform material, you can think of it as a sort of a series R. So let's say this entire material was R, then you can divide them into 4 equal pieces, and then the 4 equal pieces will basically be R by 4, R by 4, R by 4, and then just applying voltage division rule, you can figure out that, okay, if this is V, this is ground, then this is 3V by 4, this is V by 2, this is V by 4. And, in the last class, we showed that if I plot this now, then the electric field is actually linearly varying also. Now, the thing, this is a little bit of a simplification because you can ask like, oh, there are charge carriers in it. How did you apply this? Why didn't you apply the Poisson equation? Actually, yeah, you should. And if you want to be rigorous, maybe, but it is charge neutral in the sense that even if the electrons are flowing, whatever is flowing here, they're getting out here, in the sense that any cross-section volume I take, they're still charge neutral. So I can almost apply the same principle like before. So if the potential is varying linearly, then the electric field is obviously constant in it throughout this phase. And if it is constant, then if I take any electron here, the force is on the electron is Q times that electric field, because the electric field is uniform. So I can kind of take anywhere in that block. But like I was explaining last time, although it's a force, it doesn't accelerate continuously. It kind of bangs around because the crystal lattices, they're like speed bumps. Like I think it was Chandan who gave a really good analogy, like it was speed bumps. So it's trying to accelerate like those motorists in our roads, but you put speed bumps, so they just kind of keep bumping, and then you have like an average velocity. And that average velocity is proportional to the electric field, and that proportional constant is called the mobility. So for every material, or especially in semiconductor material, that mobility you hear about is basically that proportionality constant. And this Vd is the average velocity of the electrons, okay? So if you know that, the way to calculate current is, like as I said, since this is a uniform material, I can calculate the current in any of this branch because the KCL needs to be valid, right? So I can apply KCL here, or I apply KCL here or here, wherever it is, it should be. So I can take any cross section here and whatever is the current flowing through that cross section is obviously the current flowing in the entire network, because the KCL still needs to be valid, because there is no charging element here, no storage, charge storage element here. Okay, so basically what I'm doing is I'm taking a cross section area, finding out the unit length, charge density per unit length, and finding out what distance it travels per unit time. This entire enclosed volume is the total charge per unit time, and that gives me my current, right? So the average current is equal to the charge density per unit length times the velocity, because that's dx times dt. So that gives me the charge over the unit time. So if I just expand all that, I know the charge density uh, uh, from the dopant concentration plus the area and the height. So like I said, usually we don't worry about height in VLSI. It's a two-dimensional structure. So we are only worrying about W and L. So we're just looking from the top here and basically saying, what's the charge density? And we take the charge, unit charge length times W. That gives me, sorry, sheet density per unit area times W gives me the charge per unit length. So basically it's a charge per unit length here, the QS times W. And then I multiply that by VD. That's my total charge in this volume per unit time, which is my current here. So if I expand the entire thing, this is the relationship I get between V and I. And if you look at this relationship, you can see that this looks like a block of material when you're trying to calculate the resistance of a material with some sheet row of a material, because this is your sheet row times L over W. Okay, and like I always say, you should always do a sanity check to see if this is making sense. So this is your effective resistance of that block, which is inversely proportional to the charge density, right? Which makes sense, because if I have more charges here, I'll have more charges per unit area. That means more current, which means less resistance. So that should be inversely proportional. Inversely proportional to mu, because velocity is proportional to mu. So if mu is high, velocity is high, that means more current per unit, more charge per unit time. That means the resistance should be lower. So that should be inversely proportional as well. Inversely proportional to W, because if I increase this W, then I have, let's say I increase this W by 2x, I have twice the amount of sheet charge, which means that per unit volume, there will be twice the amount of charge, which means twice the amount of current, which means that effective resistance looks half now. And directly proportional to L, because if I increase this L, like again, Chandan gave a really nice example, because since you're going through that humps, now you takes twice the amount, it goes through twice the amount of humps, so your effective charge per unit time goes into half if I increase this length, and that increases the resistance. So if I make this 2L, then my resistance will go up by 2x. Okay, so we're going to use this when we derive the current equations for the MOS transistor. So instead of doing the classical way, we'll just take this expression and just put it straight into the MOS equation. So that'll save us some time. So any question on this one before I show you the MOS working, the threshold voltage?
Sir, I just need to just ask
Yeah, go
one
ahead.
thing.
Yeah,
So
sure.
there is mobility. You are mentioning like mobility. So in interview, mostly sometime interviewer is going to ask like, okay, why there is a difference in the mobility of electrons and holes?
Uh-huh.
That's one question. The second question is like in the lower technology node.
Yeah,
So what happened is, so the relationship between the mobility of electrons and holes, that is changing. So there
right.
was a time when it is like 1.5, 2 times, 1.5 times. Nowadays in a 5 nanometer, or so it now it is almost like equal.
Almost equal,
So
yeah. I think
yeah.
it started almost like 4x, I think became 3x, and like 180 nanometer is almost 2x, 2.5.
Yeah.
Okay.
So the point is like a lot of student they
Uh-huh.
have this notion like, okay, mobility of charge carriers, that is fixed, and it's not going to, so it is just like some property which is not going to change. So I'm just asking, like, are you going to cover that particular part, like how the mobility is also
I think I
having
was
some
thinking I'll
parameters?
maybe we'll do that when we do short channel effects later on. That way we can, this one I'm actually assuming that the mobility is constant for any given electric field or any material. Basically, you're asking like, why is the mobility changing with electric field, with material types, with different material types and so on, right?
Yeah, so
Okay.
I'm just asking, like, okay, if we can also just highlight that particular formula for the mobility formula, so that they will come to know it's not a constant value. It also have a dependency over two parameters.
Right. So yeah, I can maybe just verbally explain right now. So uh, obviously here in this equation, it says that it is a constant, proportionality constant. Doesn't matter what the temperature is, what the value is, and so on, of the material or the electric field. But this mobility, there are a lot of variability with this mobility. So like Puneet was saying, uh, so this is an N-type material. So let me just write it right here. So let me call this mobility mu n. Okay. Uh, if I take a p-type material, and like Puneet was just mentioning that in current technologies they're almost becoming equal. But let's take a technology like 180 nanometer, which we use in the lab a lot. If you take the mobility of the n-type material, which is mu n, and a p-type material, which let's call it mu p, of the same concentration, they are in this kind of technology now, you find it that mu n is almost equal to 2.5 times mu p. In other words, that you take the same block of material, n-type or a p-type, the p-type will be 2.5 times more resistive than n-type. Or in case of a MOS transistor, if you want to think about it from a MOS transistor point of view, the same size MOS device, a NMOS, will be 2.5 times faster. In the sense, it will charge a same capacitor 2.5 times faster than a PMOS can charge a capacitor. The other thing it depends is actually this electric field also. So it's actually not a constant. So what happens is this equation tells you that if this is my electric field and this is my mu, um, actually it's not mu and electric field. So let me say it's VD. The VD. Then it says that the VD is proportional to where this slope is mu. But it's actually not. After some electric field, this flattens out, what's called velocity saturation. So your mobility almost becomes like infinity, basically, after a certain electric field. And that is a huge factor in present technologies because this electric field is getting much, much higher because your distances are closer. You remember electric field is V times the distance, right? So in, like Puneet was mentioning, 7 nanometers. So this is 118 nanometer. This is 7 nanometer. That means the voltages are not scaling appropriately. So this is 1.8 volts. And this 7 nanometer is still about 1.2 volt. People are still operating in 1.2 volts. That means the distance has decreased it by almost, what is this, 214, almost 20x, but the voltage is only 2x. That means this electric field has gone up by 10x. Okay. So which means that you're in this region now where the mobilities are not as fast. So the mobility is hurting, or you have what's called hot electron effects and stuff like that. And the third thing is temperature. As the temperature goes higher and higher, the mobility also drops. So for higher temperature, the mobility will just start dropping. So if you want to just take away like 3 things, the mobility depends on the type of material. It's N-type, P-type. Why? That's like a little bit involved. Even I have to look. And so it's mostly to do with what's called lattice coefficients, like how much it is banging against the crystal lattices. So to understand the exact mechanism, you have to go a little deeper into that semiconductor theory. But essentially, it depends on the material, it depends on the temperature, and on the electric field also. Like once your voltage is increasing, but your distance voltage is almost remaining the same, but your distance between two plates or two wires or two, the drain and source, they're decreasing. That's also limiting your mobility, and that's hurting your speed for your devices. So that's kind of like a rough overview. I don't know if that's what you wanted, Puneet, or like a lot deeper into that. Maybe we can do another lecture
I
when we
said,
do
I
short
think
channels.
that that's a good one. So I just want to add one thing,
Yeah,
because
go ahead.
you already someone is Rajiv. I think Rajiv, can you just mute?
Yeah, somebody's.
Yeah. So can you just give me one sheet, or maybe I can just share and
Yeah,
uh,
sure. Do you want me to open like a?
I can
Uh,
I
yeah,
can
just
just
go
share.
ahead. You can share that. Actually, I'm
Yeah.
done with this slide, so I can just stop it actually.
So I just want to tell these candidates, like, okay, the same thing which you have just explained in terms of the mobility. So you have to, I think, sir, you have to
You have to.
share,
Okay. All right. Let
or you
me
have
do
to
this.
make it multiple share.
Let me bring up a whiteboard and
Yeah, you can do in that way also.
uh, can you write on this one now?
Let me try. Yes, I can do it. So guys, so just for your how you can understand, like, okay, mobility has a dependency over the type, temperature, and material. So I will just give you a very short thing. So like, there are the electrons, there are holes, and all of you know this particular part. Like, when we are talking about any particular crystal, so like, so I'm just giving you an example in terms of like how you can understand and you can remember this thing. So if it is a n type, so in a n type, what is going to happen? Like, there is a extra electron. So when I'm saying the extra electron, so remember with the covalent bond. So the this extra electron in a n type, so it is not a part of a covalent bond. So if it is not a part of a covalent bond, then it's very easy, uh, like, okay, you can just give a small energy, and you can just free up this particular electron, and it can conduct from one place to the another place. So let us suppose this electron is right now associated with this atom, or maybe this particular bonding. So it is a part of this thing. Now if you will just give a small photon, so like, I think photon we usually draw let me just write it here. So if we just give a small photon or a small energy, so if you will give it, then this electron can just move like this. So just remember in this particular way, like, okay, how electrons can move in a n-type semiconductor. Now similarly, it's the same structure if I will draw for PMOS, and I just want to show you in terms of again the same covalent bond. So now here, if I'm saying there is a hole, that means in this, so let me just draw the electrons also, like in the covalent bond. So in a covalent bond, what is going to happen? Like, okay, this, so it has all the 4 electrons, but here there was only 3 electrons, and then all rest, I'm just talking about all the 4 electrons are there. So what is a p type? Like, there is a deficiency, you can say, like, okay, there is a 1 electron is missing, and that electron is like is that become a hole. So you can say, like, okay, there at this particular place there is a hole. Like, that means if there is any electron, then it is hungry, I would say. Whenever the electron will come, and it will come at this particular point. So as such, the hole is you just remember like a hole is basically like, okay, electrons is not there, and if holes are traveling from one place to the another place, that means somewhere else some electrons may be traveling. So maybe the electron is, so there is one electron here at this place, and let me just draw this one with the blue, not the blue, the yellow one. So when this will come here, that means you can see like, okay, this hole is basically traveling here. You can say in that, and you can say in that particular way. So just understand, just for the understanding purpose, there are a lot of device physics behind that. So, but here what I'm just trying to tell you, to move this electron from here to here, that means here again you have to give some photon, some energy, and that energy which you will give, it is going to like break covalent bond, or you can say that you need more energy so that the electron will come out from the existing covalent bond, and it will just jump from here to here, and that's the way the hole is going to flow. And what is a mobility, like sir explained it, like we were talking about in terms of average velocity, and then we are talking about mu p and the electric field. So I think now you can understand, like when sir was explaining you in terms of the temperature effect, obviously. So the temperature in the sense that, okay, first let's take about the type of material. So it's the n type or the p type. So you can understand the n type, what is happening in n type. The electron is flowing, which is loosely bound with the atom, because loosely bound in the sense it's not a part of a covalent bond. In a holes, basically holes is traveling because it's a part of a there also the electron is flowing, but there the electrons are those electrons which is a part of covalent bond. So you need more energy to transfer the electrons which is a part of a covalent bond, and you need a less energy to transfer electron which is not a part of a covalent bond. That means with respect to the type of material, the mobility is going to change, because the mobility is basically this relationship we are talking about. Similarly, in terms of the temperature, now you can understand, like if you will increase the temperature, that means you're giving more and more energy. So that's how if it is more and more energy you're giving, then you can understand, like, okay, how the more number of electrons, and you're just giving some other forces. And similarly, like the third one is a yeah. So I think sir was just telling in terms of the electric field also. So electric field is also like type of force, the type of external energy which you are going to provide these electrons. So you can give the forces in a two or the three different ways. Like one is temperature. You just increase the temperature. That means you already giving them certain energy, and then the moment you will apply the less electric field, they can just move, because now the less energy they need to jump from one state to the another state. And similarly, the temperature, or maybe you can just give some photon, or if you will just increase the impurity also, then also it has a dependency. So just to understand, if anyone is going to ask you in terms of the mobility, maybe now you can have a little bit idea, like, okay, how mobility has a dependency over the temperature, how the mobility has a dependency over the type of material, and why it is different for p type, why it is different for n type. And there is a one more, like in terms of a distance, like that sir already explained you in terms of like the electric field, and the forces and the voltage which we usually apply to that as a particular system. Yeah, that's all, sir.
Okay, thanks, Puneet. Yeah, that's a great explanation. Yeah, so I guess to summarize, in case of a n, the electron is free to move In P, you're breaking a bond and releasing, so it takes extra effort to do that. Actually, Puneet, I haven't looked into it. Maybe you know it. So why is it becoming equal now for the lower technologies?
So,
Maybe,
okay, so there is a one more thing, in terms of you were explaining that particular part, if I remember correctly, it's all about the random motion which we are talking about.
oh, I see. So the
And
lattices, yeah,
yeah, so what happened, like when in a higher technology node, so if we are talking about this, so we usually average it and we will say like, okay, the electrons are moving like this,
right.
electrons are the holes. But as you're going to decrease the dimensions, so this the effective motion, or the in one particular direction, that's going to be decreased. So because now what is happening, if I will just zoom it and if I will say like, okay, so what is happening in this area, it is just traveling this much of distance. Means it is traveling more distance, but effective distance is the less distance.
Yeah.
So that's the something affect that particular part, and it is on a P type and an N type. That motion, if you will see, uh, it's
So
it's
basically, you're saying it's not getting averaged as much because the distances are so small.
yes.
They're almost looking the same. Yeah.
So basically,
Okay.
the theory which we are talking about right now in a 180 nanometer, or a large nanometer, like we are just ignoring this particular part,
Right.
but we are just averaging it out, and we are saying, okay, it travels this much of distance with this
Right.
particular force. But on a lower technology node, as the dimension decreases, this thing come into the picture. Now how that is going to translate into like making both the things equal,
Right.
that even I'm not 100% sure. I didn't did that much of
Yeah, I
research.
haven't looked at either. But yeah, it's been definitely dropping. I mean, I haven't worked anything beyond 130. 130 is almost 2x now. But yeah, lower technologies, I think you're right. It's almost equal now.
So there,
I think
these things also come into the picture. Like in some book I have read, like in some research paper, I think, like there was some equation basically. Like
right.
they were just explaining like, okay, now the equation is different in terms of the mobility. So the mobility also, they have some two parameters, I think two or three parameters are there, where they were talking about some, I don't remember those two terms. So those
Ye-
things changes basically.
Right, right. Okay. Maybe, yeah, when we do like short channel effects, if we cover at some point of time, we can maybe cover that
Yeah.
a little bit. And it'll be good learning experience for me as well. So,
So I thought like, okay, this particular part, because what happened, like if these candidates is going to check and the internet and everywhere, then they will see a lot of people they are talking about in terms of 1.5 and the two times. And when we are going to discuss in a CMOS, then we will
right,
talk about like, okay, why there is a different width of PMOS and MOS. So I thought like,
right.
okay, we will just
No, that's good. Yeah, actually, it was good. So, did everyone understand what we are talking about, like the mobility difference? Is everyone getting what we are talking about, or any questions? Okay, Punyadev, yeah, looks like you have a question. Go ahead.
So, like you have said, we have to provide in N type there is an electron, and in P type there is a hole.
Yep.
So we have to provide energy to both of them for conduction.
Right.
So P type will definitely will require more energy than N type.
Okay.
So why P type semiconductor exists in the first place? Like we always try to like to create devices
Wow.
which are energy efficient. So
That's a good point. I don't know, Puneet, you want to go ahead with this, or? Uh,
so, first of all, I didn't get the second part of the question.
oh, he's saying what he's saying is that Okay, you just said that the N-type conducts really good with, so he's saying low energy. Basically what it means is given voltage, you get higher current, right? For a given area, W over L, you get lower resistance. Why use P-type at all? We always want higher efficiency. Why use a P-type at all? So good question. So yeah, I thought
Okay.
maybe
So
you
if we will talk from the MOS perspective, okay, CMOS perspective. So
right.
okay, so for me personally, if you will ask me like, okay, just use only one type of material, one type of semiconductor. So then you will see like people are using NMOS. So for example, the memories. So if I will talk about 60 memory, so you can just go and just check it like in a RAM, SRAM. So there are the architecture of the 6 transistor, 8 transistor. Everywhere we are using NMOS, because initially in the long, I would say like in a history, there was from the mobility point of view, they are fast. So in the memory, we are all these structures are basically more or less in terms of the NMOS. Nowadays you can say like, okay, nowadays it can be PMOS, but traditionally we are using NMOS. That's the reason we are using NMOS. When it comes to the complementary, where we are using PMOS and NMOS, they are basically the purpose of using PMOS is a different, because the property of NMOS or the PMOS, when we will study um, their working, then you will come to know at one logic level, one is going to be off, in another logic level, another is going to be off. And so that's the reason their name itself is a complementary. Like when one is working, another is not going to work, and when the PMOS is working, then NMOS is not going to work. And that's the reason we are using PMOS. But always, like if anyone is going to ask you, so there are a couple of questions where we will ask you like, okay, which uh, material, which circuit you are going to use, and then definitely on the basis of the NMOS and the PMOS, how they are structured, on the basis of that you will decide, you will say like, okay, uh, if you need a fast logic gate, then you will come up with the structure. When I'm saying the structure is a schematic, I'm talking about like which has a NMOS. So so the short answer of your question, like we are using PMOS because of the logic levels. We want to operate that particular device in a one particular logic level. And if you will ask me just use one, so I will use NMOS.
And just add like a little bit more like a philosophical thing in the sense that we don't always want only fast devices in a circuit, right? There might be times when we want a good resistor. So if I want a good resistor, I want to use a P-type because for less 2.5x less area, if the mu's are 2.5x area, I get the same value of resistor. What I mean is like, let's say I want in analog, especially in digital, we definitely not always don't need a resistor, but in analog for example, we need resistors. So if I want a high value resistor for a given amount of area, then obviously I want to choose a P-type because that will give me 2.5x area advantage, which is in semiconductor, that's huge. And also, like for example, if I can Puneet, if I can just quickly draw here. Can I draw here? Okay, so one second. So let me just add another one. So in chip design, all your circuits are in one base, right? Everything is in one what's called a die, right? So let's say you have a NMOS here, you have a NMOS here, and you have another transistor here, for example. So these are two transistors, right? There's a MOS here, there is a MOS here. You don't want them to talk to each other unless you want to, and which means that this base material, this body of material you want it high resistive, high res, and that's why you use a P minus, because because the area is fixed, right? You want the minimum area between these two and the highest resistance between these two, because you don't want these two circuits to be shorted by a resistor here, a short resistor. So in that case, I actually want this to be a p-type material, not an n-type material. So depending on the circuit, we might need a high resistive material or a low resistive material. But what Puneet was saying, for example, in a CMOS, like if you remember that first gate I showed you, that we want a switch from VDD to the output load or charging this. This one, it is efficient to have a P-type. This is efficient to have a N-type. When I say efficient, we don't need extra circuitry. Just with one switch and the same control voltage, we can do that if this is P-type. But obviously the penalty you pay is that this is 2 times slower than or 3 times slower, or now like Puneet was saying, they're almost equal, so they don't matter. I think that's all I wanted to add to that.
So now you said that they're almost equal. Means how it is equal?
Yeah, so I would say like that's the one thing. Maybe
Yeah,
I
maybe we
have to
can,
check it. Yeah.
right, we can come back with some more material on it, or give you some reference material to you to read.
So that's something like
You
you
can
you
search too.
yeah you can
Right.
search too also, but that's it's just a eye opener for you. Like okay, now we have almost equal thing, and that has a something related to the distance in terms of the size of the device. So like can I just give an idea, like okay, just a hint, it is something related to the random motion of electrons and holes. And but yes, proper explanation maybe even I have to just check it once.
Yeah, even I can't comment. I haven't looked into it yet. All right, so Prachita, looks like you have a question.
Yes, sir. Sir, here that PMOS will be acting like a resistor that between the two
So,
NMOS if you don't want them to come in contact with each other.
sorry, I couldn't get the complete
Resistor.
question. Okay, can you repeat it, please?
So yes, you mean that by adding the PMOS inside the two NMOS, so you said that we want to isolate them as long
No,
as we don't
not
want
not
them to
not
connect.
not adding a
So
PMOS.
we are
What?
connecting the
No, it's a P substrate. It's called a P substrate. So the entire chip is in one
P
substrate.
substrate.
It's like your PCB, right? You have a PCB when you're making like some electronic device. That PCB is an insulator, right? It's a FR4 insulator, because you don't want circuits to talk with each other and be shorted. It's the same thing in IC. We can't use a PCB. We use a P-type material, and that's one of the reasons we use a P-type material. Is it's actually very resistive in nature, so that we are not shorting all devices. Okay, go ahead. So go ahead with your question. So what was the question again?
So I thought that was a PMOS acting as a resistor in between the two NMOSes.
No,
Like
no, no. That's the entire.
we
It's
need
like
a
the
resistor.
PCB. Right, it's like the PCB.
Yes.
So when you're doing a PCB, for example, the reason
Yes.
you choose FR4 is because it's a very good insulator. In this case, we cannot use insulator. Actually, we do now, the SOI process, silicon on insulator. That's how they do it. They actually put all the devices on glass, actually literally on glass, so that's it's insulated. But the cheaper processes or the older processes, they're still done on a P-type material. So all the devices, even the PMOSes, are done on a P substrate, where you first do a what's called a N-well, then put the PMOS. For the NMOS, you just straight put it on the P substrate. Okay.
Sir, and the temperature, high temperature, you said, sir, how do
Right.
you going to increase adding more of photons and
So
what
at
other
uh,
processes?
at high temperature, the mobility actually drops. So it becomes more resistive.
Yeah, okay.
And so it's a fight between two things. What Puneet was explaining. So for example, if I um, go back to Puneet's slide here 1 second. So like what Puneet was explaining, these electrons, they're moving, but they're banging against these electrons, right? So they're like the bumps, right? So as they're moving, they're bumping into this this structure and so on, and that average speed is what's called mobility. Now at high temperature, what happens is, like when you said, this has more energy, but the problem is these are also vibrating more. Now these guys actually vibrate more than these guys have energy. So when these guys are vibrating, so for example, we are showing one atom like this, but they're actually vibrating all over the place like this. So when this electron is trying to travel, it bangs, and then this is vibrating, it bangs, and this atom is vibrating, this bangs, and so it slows down further because of the high temperature. Okay, so at high temperature, this electron has more energy, but these lattices are vibrating even more than what this has energy. So it starts the Brownian motion we talk about, like just banging into the walls. Um, that is more often now at high temperature than at low temperature. Puneet, you wanted to add anything to that? Or
No, sir. Good. So even maybe after this call, I will share with everyone one article. So that is going to help you to understand, like, okay, what exactly we are talking about, the mobility and what are the other things also.
sure, that'll be good. Hey, I can put it on the Moodle page for
Yeah,
reference as
so
well.
that's basically the discussion, the same question, like why the mobility of holes is different than the electrons. I think if you will
Yeah,
just go through the couple of answers there, so everyone is from the different universities.
right.
So you will able to understand, like, okay, the different aspect of this mobility thing.
Okay. The only
So
thing I
then,
want,
what
yeah,
was that shortcoming?
yeah. Go ahead.
So then, he sir said that what was the shortcomings now we are facing about designing a chip in lower technologies
Shortcoming
about
for
that
what?
180. So that if we design it in like if we see as a whole it is 180 nanometers, but the lattices are placed very closer to each other, so no space. Sir said something like that.
So
Puneet sir said that.
Yeah,
yeah,
go
so
ahead, Puneet.
Prakshita,
Actually, I
I would
didn't
say,
get the
like,
question.
I will just say, just hold on all these questions. Okay, so maybe we will also get more clarity, and then we will just tell you, and
Yeah,
or whatever the article, the question answer I'm just sending you. Maybe just go through that particular part, because at this stage, the reason I just highlight this topic, so that you all of you just start thinking. And
right.
even I'm not the expert in this particular field, even I have to do some research on this. Okay.
Yeah, so I think once Puneet sends some reference material, you guys can take a look, and then maybe one of the lectures, maybe 15, half an hour, we can spend discuss about it if you have any questions. That might be more helpful. Okay, Punyadip, you have another question, or
Yes, sir.
yeah,
So like you said, when the temperature rises,
yeah,
the electron keeps on banging in the crystal lattice and then
yeah,
slows down due to
yeah,
loss in energy. But
right.
this loss in energy should be compensated by the rise in temperature through which the energy is being supplied. So why
No,
the
no, no.
average speed decreases?
Uh, that's a good point. So basically, you're saying it's banging, and that should go as a heat, right, to outside. But that's being lost
Yes, sir.
as heat, right? So one
Yes.
is you're providing heat. The other one is actually emitting heat. They're two different things, right? So for example, you have a resistor, right? If I heat up a resistor, then it'll do what do you call it? It'll drop the current flowing through it. But if I pass a current through it, the heat is also I square R. You see what I'm saying? So
Yes, sir. Yes, sir.
they're reciprocal, right? So what we're talking about is if your temperature from outside increases, then the
Hmm.
resistance actually increases. Yes, the heat increases because it's I square R, because it has to
Yes, sir.
emit, right?
Yes, sir.
So they're reciprocal. So if I take
Hmm.
a resistor and just pass a current I square R into it, that's heat, right? So
Yes,
if
sir.
my resistance is increasing because of the bumping, then I should have heat also. But that's not the heat giving energy. That's the emitted heat, right? So they're
Yes,
two
sir.
different things.
Hmm.
Okay.
So that banking giving extra amount of photons or exothermic reaction to take place, so that heat is not used. Like we are giving separate heat for that giving.
Say that again. Sorry, I couldn't hear you.
Sir, if you give the photons, so Then exothermic reaction will also emit it as Punil said. So, sir, that heat is not used. Only the heat we provide separately by some other source that will be used for the mobility.
I'm not sure I follow. Puneet, you follow? You want to answer that or?
No, sir. So even I didn't. Uh, I'm not able to understand the fully thing. So if I am able to understand,
So,
she was just saying like, okay, the amount of heat which we are going to give, like or to provide,
Yeah.
that will emit as a heat energy. Then how come the speed of the electrons or the lattice that is going to vibrate? If I understood correctly, sir.
yes, yes,
Okay.
yes.
Oh, so you're saying I give heat. How is it emitting heat outside, you mean?
So what she is saying, like
Yes, sir,
we are
because
giving
it's
heat.
an exothermic reaction.
Yeah.
So if we will give the heat, it will emit the heat. Okay, and then that means it's neutralized.
No, no,
And
it's
then
not near. No, that's what I was trying to explain there. Like if you take a resistor, for example, you heat the resistor, for example, the resistance increases, but that I square R, which is dropping, that's the heat is emitted, right? You can't, they're not equal. They're not canceled, right? They might be different depending on the resistance. Like for example, some resistance may not increase the resistance at all, which means that it'll just heat up by that amount. But if the thing drops the resistance so much that the I square R is high, then you'll have lot more heat. It'll depend on the material, right?
so, sir,
Yeah.
if you just give me one more slide, maybe I can just
Yeah, sure.
help all these questions. So I think you guys, the questions which you are asking, that's good. But
Yeah, go ahead.
if you remember, so like I'm just going to explain from the photon and from the perspective of the atom. So the point was, if you remember, I just mentioned this is a one atom, and there is a electron associated with this atom. So when I'm saying associated, that means there is a energy, there is a some force. Let us suppose like because there is a nucleus and that nucleus is going to attract this particular electron. Now similarly, there is another atom, and this electron, what we want this electron to move from here to here. Now, since this electron is already part of this atom, the atom A, if I will say, and this is the atom B. So, from the energy point of view, so if you guys remember, there is physics maybe in the 12th or maybe in the first or the second year. It is like if you will give a photon, that is going to give a energy to this electron so that it will just come out from this force. But so what is happening, the electrons is now somewhere here, this electron basically somewhere here. That means it is this electron come out from the force, the attraction force of atom A or the nucleus A. So that's the purpose of that particular photon. But again, if this electron has to go here, so that means and here it has to come again here, so then it has to emit that particular photon. What you, if I understood correctly, everyone was asking the same thing, like okay, some energy we are giving, some energy we are getting, then how the electron is going to like the movement of the electron or the crystal vibration, all those things, how it is going to happen. So from the photon terminology, this is a part, like okay, this is an intermediate state, like your electron with the help of a photon, this goes here, then it will come back, and here it is going to emit that particular photon. So at the end of the day, it looks to you like okay, you gave one photon, you got the one photon back. Now in the terms of the temperature, you can just understand like okay, I'm increasing the temperature, and that is there is a energy of the temperature is heating, then where the movement is here. See, so that's the reason, like energy cannot be created nor be destroyed. So if you're thinking from that particular principle, I hope that helps all of you guys.
Yeah, I guess everyone's
Yes, sir.
this is like
Sir,
equal sum. Yeah, go ahead.
Yes, Shatabdi.
sir, if we consider the effective amount of electrons less than the holes, so if but the relaxation time will also be small for electrons. So you said some cases mobility of electron in the hole will be same. So how it will be possible then?
So, Shatabdi, for this particular question, you have to just wait. Okay. And we will come back with the exact answer. Okay. So that was just for a just to poison you guys. Like, okay, this is the thing. So I know, like, now all of you are curious to understand. Even we are also curious to understand. So we have a vague idea. That's what we explain, and that's not going to answer this thing. That's not going to help you out. But I think just keep this poison for a few days, and if you are curious enough, just go and read the articles. I just message one articles that is going to give you more understanding about like whatever we are talking about. So my suggestion is like, okay, I poisoned all of you, and now what you have to do, whatever the curiosity you have, you just read, and maybe you can come up with the explanation, or maybe we will come up with the explanation.
Okay, Punyadeb, you still have a question or
Yes, sir.
okay? What's the
So,
question?
as Punit sir said, there are two atoms A and B here. So we need to provide energy for to this electron so that it will come out of the influence of that atom,
Hmm.
and it will go to atom B. So like we have to determine a point where it is out of the influence of atom A, and still atom B is attracting it, so that when the energy it emits energy, it will fall back to atom B.
Uh-huh.
So how this all process is being controlled and managed?
So that's a device physics, I would say. That's the something is like, you can, from the analogy point of view, you can understand like there are two planets, and so you cannot you have to be bond of with respect to the one gravitational force. So that's a something in a device physics, like an electron, suppose. So there are energy states. So, and there is something looked like as a free, like the infinite one, like, where electrons is out of all the attraction forces from all the atoms. And that's the five which sir explained you guys. Like, okay, they, from all the energy band, if you will just free up that particular electron in a open space, so that is a five thing. But that's never going to happen, like, okay, a particular electron, you just remove it, and now that electron is not a part of that particular crystal. So that's going to be the part of a crystal only. And if it is come out from the crystal, then it is basically like, the whole crystal is going to be positive charge or the negative charge. So when I'm saying the charge is going to be like ions, we will talk about in that particular way. So right now we are just talking about the crystal related thing. Within that particular lattice, whatever the electrons is moving, it will come down, and it will be the part of one atom or the another atom. So that will be in that particular way only.
Yeah.
So what is the mechanism, and how we are going to control it? I think I never control it. I never read it somewhere like, uh, at least from the VLSI point of view, we are controlling it. But yeah, from the research point of view, people even are controlling the spin of the electrons. So but I think that's a totally different area in terms of the research. And I'm not expert in that direction.
I guess I can, you can explain it through band diagram real quickly. Like, I don't know what type of question was. Like, for example, you remember the valence and the conduction band, right? For silicon, for example, is 1.1 electron volt. So
Yes.
you have electron here, you get a photon with h mu, let's say, equals to 1.5 electron volt, right?
Yes,
So
sir.
it has enough energy, it will go here, but what happens to the extra 0.4? Well, that extra 0.4 is for to move around. That's the kinetic energy, right?
Yes.
So 1.1 takes the potential energy. That extra 0.4 is kinetic energy. It's moving around. Like as I said, Puneet said, as it is moving around, it found B and it dropped. But when it dropped, this 1.1 has to go somewhere, and that goes as a photon back. But something will be lost in heat and all that, and it is very complex, obviously, like Puneet was saying.
Oh.
But maybe this is, I don't know if that's what you were asking or like.
Yes, yes.
Okay.
Sounds like-
Okay. And I think there was another question by Saurav on the chat. I'm not able to get CV characteristics of MOS capacitance at different frequency and different voltages. So different voltages obviously we'll cover after we do the MOS capacitance. But then the frequency part is, that's like RF stuff. Usually we won't be covering in the digital, but we'll see. Maybe we can do a little bit of that in some lecture. But I would hold off on that for now. So the voltage one we'll cover once we have done the MOS characteristics, like how the charge is formed, basically in the next few lectures. Okay. All right. So we're already at 6. So maybe see. So that's it. Puneet, did you want to say anything or?
No, sir. So I think I already
Okay.
poisoned these people a lot,
No,
actually.
that's good poison. That's good poison. So, all right. So let me see. Maybe I can quickly give an idea, and then next class we'll do the IV characteristics. Okay. So I think I covered it last time. So let's 6.5. Let's take like 10 minutes and go through this, and then that way you can just kind of put together everything, and then we'll continue next time. Oops. Sorry. Okay, guys can see my screen, right?
Yes, sir.
Yes.
Oh,
Yes, sir.
saying desktop is paused or resume share. Okay. All right, so I'll go through, I think I kind of explained this a little bit last time. So everything we talked about, we'll try to put together to go over the threshold voltage concept of MOS device. I think I gave you an sort of a motivation last time. Why are we doing this? For obviously to do a switch. But before we do switch, we are trying to, and I showed you like, for example, a FET device, like controlling a depletion through a field effect. And we said that's not good for doing IC because the density is low. We need contacts on both sides and so on. And so that's how we said, okay, let's look at a MOS device, which is used, and just the MOS sandwich, metal oxide and a P-type sandwich, and see how we can control a channel through the voltage, and then we'll see how to conduct current through it after that. So we'll just look at the channel formation, which I kind of quickly went through it. We'll also quickly go through it again, and we'll quickly go through it again next time. So if you take a metal, so this metal can be like what we've been saying, polycrystalline. And then oxide, which can be silicon dioxide probably, and P-type semiconductor, and then apply a voltage from the metal to the P-type, let's call it VG. When you do that, what happens is positive charges starts building up on the plate, and because it's oxide, the electric field goes and ends in the P-type, but the P-type doesn't have negative carrier. The majority carrier is holes, right? So it pushes away the holes. So if it pushes away the holes, it leaves a mobile carrier, and the electric field ends in those mobile carriers. And that forms what's called your depletion region, just like in your P-N junction. The P-N junction depletion and this junction looks exactly the same, except here it's through an electric field, through oxide. There, the electric field is because of a immobile charge on the other side of the junction. Okay, so if I now plot the potential through it, and I'll show you what's the key in what's called the inversion of the channel. Basically, what we are wanting is, this is a p-type material, but we want to invert this part of the channel, or any part, but it so happens that it'll actually, let me just show it with this. So we want to invert this part. We can invert any part, but I'll show you why this part is crucial because of our planar structure. This part to an n-type. So essentially what we are trying to do is, through a voltage, we are trying to control the type of material on this side. If we can do that, then we have a switch or a voltage control resistor, and then we can do other stuff to conduct current through this. So that's the main goal, is basically we want to do a voltage control material change. So we want to convert from p-type to n-type here. So if I look through the voltage, so I have these two sort of bars here. So let me first draw this one. So apply some VG, let's say. So as this is oxide, this voltage is going to linearly vary till this point, and that potential, we call it the surface potential over here. Okay, and then from here it kind of goes in that parabolic fashion, just like in the PN junction. In the PN junction depletion, you see how the potential drops like parabola, right? The key to changing this type of material is, if this potential on this surface here becomes equals to 2 phi f. And I explained last time why 2 phi f, because the Fermi potential is phi f below the intrinsic Fermi potential by phi f. So if I want to invert it, I want to go 1 phi f above, right? So this potential goes above this line, this will change to a n-type. So I increase the voltage a little bit more, the depletion goes more, this voltage goes higher. So I'm plotting this voltage parallelly as well. So as the gate voltage is increasing, the surface potential is slowly increasing. I want to get to here. So I increase it more. And then I apply a little bit more gate voltage, then this potential is exactly 2 phi f. At that point, what happens is this part becomes a n-type. Okay, so you form a channel here. So if I apply a KVL around this loop, so whatever gate voltage I apply, it is going to split equally among, not equally, split between this oxide, this voltage V oxide, and I'll show you what that quantity is, and this potential called surface potential, because let's say this is ground, then from here to the surface, it's this potential called phi s, and I want this to be 2 phi f, and then this channel will become inverted. Then after that, as I increase the voltage, this channel potential remains constant, just the electric field starts increasing. So basically that potential at the channel gets almost pinched, and then it just looks like a capacitor. So after that, whatever voltage, whatever positive charges I put, the negative charges will form here instead of going into this depletion area. And then I can use two contacts on these two sides to actually conduct current, which we'll see later. Okay, so now the definition, so this is called the threshold voltage. So the threshold voltage is basically this voltage of the, I call it G because I'm just kind of building it up to the MOS device. So basically the voltage at this metal with respect to this substrate, when that voltage is such that this potential with respect to this ground is 2 phi f, that's called my threshold voltage. So in other words, this VG is equal to VTN when this surface potential here, or this potential here, or this one here is equal to 2 phi f. If that's 2 phi f, then what I call is my channel is inverted now from a P to an N type. So essentially what I have is a voltage control switch. So I did a switch where I converted a P-type to N-type. So obviously if I have two N-type materials here, it will be resistive when it is P-type, it will be conductive when it is N-type, which I'll show a little later. So, so that voltage VG when phi s is equal to 2F is called the threshold voltage. In this case, I call it VTN because this is actually a part of NMOS. I haven't drawn the drain and source, but it is part of NMOS. So what is that voltage? It's the voltage which I need to build across this capacitor to fill all this charge here, the depletion charge, plus this voltage to be equal to 2 phi f. So basically this voltage plus this voltage here. And what is this voltage? That's the voltage just before this channel is formed, which is this depletion charge here. Okay, that's this depletion charge here divided by the oxide capacitance, unit oxide capacitance here. That's the voltage I have to apply here to create this just at the point when this is going to invert. And then on top of that, I have to apply this 2 phi f, which is this quantity. Okay, and I call this VT, and this expression, obviously we did that entire derivation using all that Poisson function and cos theorem to derive that. So that's why I wrote this equation directly. So this is the same equation, except that instead of the built-in potential, I have 2 phi f because that's the potential across these two. And if you remember, I did that approximation where I said, oh, one side is just so P plus that it is just a channel. So that's the approximation I'm using here. Okay, so basically this charge divided by the Cox is the voltage I need across this capacitor plus 2 phi f across this. That's this voltage here. That will invert the channel almost. And now I say ideal because I need now what's called that contact potential. Because if you remember, we did this discussion that before you put any voltage or anything at all, if you just did this to sandwich, there is a potential formed between these two contacts, which is the work function of this gate material minus the work function of the semiconductor material. And this is what's called a flat band voltage. And if you guys remember in that first lecture, I showed you the band diagram where when the band diagram was bending, you apply a voltage to first flatten it before you apply any of these voltages. So that's why it's called a flat band voltage. And I won't go deep into that now, but just any book you read, you'll be able to understand with the reference to the band diagram. So I would say, just do some self-study on that. And that happens to be the contact potential as well. Okay, so that contact potential we talk about. So a lot of places you'll just see it's referred as a band voltage. So basically I have to, on top of, and that so let's say this was a p-type polymetrial or an n-type polymetrial here, which was doped with some dopant capacities Nd. Then this phi gs will be this quantity here, which is the thermal voltage times this. And if you remember this, this is actually the same as the built-in potential of a diode as well. So the discussion we were having, that is it same as the built-in potential, in basically, yes. It is kind of the built-in potential. So you have to first provide that potential and undo this bit-lit potential, then apply these two quantities here. So you basically first apply this, what's called the flat band voltage, then apply these two quantities here. And once you apply that across the gate and the substrate, this channel here is going to invert. Okay, so I'll take an example. So I take an example where Cox is 3.45 femtofarad per micrometer square. So that's the oxide capacitance here. And let's say I have doped this p-type with 10 to the power 15. So it's what's called lightly doped because that's what I want usually for substrate. And then this one I have heavily doped 10 to the power 19 because I want it like almost close to metal. And why don't we have metal? Why don't we just put metal? That's a processing question. Maybe we'll answer sometime else, or I can answer now if somebody has a question. But that's the poly type. So if I do the calculations, the flat band turns out to be minus 0.865 2 phi f. If I use our earlier Fermi potential, that Vt times ln over Na over Ni, that turns out to be 0.579. And you can see the depletion voltage is actually very small. It's usually a negligible quantity. If I add that up, the VTN turns out to be negative voltage, minus 0.25 voltage. In other words, it is actually conducting even when I put a zero voltage. Okay, and as I put higher and higher voltage, it conducts more and more. And this is what's called a depletion mode device. Now, typically in a IC, because I have 0 to VDD, I don't want dual supplies and all that. Let's say 0 to 1 volt or 0 to 1.8 volt, I would typically want this to be a positive quantity. So for example, let's say I have a 1.8 volt technology in 0.18 micron technology. This I want it like, let's say 0.6 or 0.5, something like that. So that, so this is what's called the intrinsic VTN. So if you just take the p-type, put a oxide, put a metal, this is what you get VTN. Then what is done is what's called enhancement. They engineer it, so they actually implant some ions in it. So in this case, there'll be negative ions in it. And ions, because you don't want to be free flowing electrons. If you have free flowing electrons, then it's a short, right? It's no noise. So they have to be immobile so that they're not conducting in this direction. But I require a extra gate voltage to come back to this value, to come back to this value. So in other words, I'll just show you the expression. Um, so basically what happens is once I put this implant, then the VTN expression is all that was before, but now I need to add an extra voltage over here to get this potential to VF so that it inverts the channel. So essentially it's a controlled implant. So now, like we take the example, let's say I put, for example, in this case, 2 to the power 10, 12 ions per centimeter square. So I put in this thin area, I put so many ions. So then the voltage I need to first nullify it, to neutralize it, is basically that charge divided by this capacitance here. So I need about 0.928 volts. So if I use the previous expression and add them up, now the VTN is 0.678 volts. So with this implant now, I need to apply at least a 0.678 volts before the channel is formed here. Okay. Um, and there is another quantity here, which is this. So if I write the total expression for VTN, it's your flat band voltage, your bulk charge inside the depletion. This is your 2VF. This is what's implanted. And this is called impurities. So I've been saying that there is no charges in the oxide. That's not true. When they manufactured, there is always some sodium or potassium ion gets into it. So there are some charges actually lodged into the silicon dioxide. So I have to undo that as well, either positive or negative, depending on which charge. And then there's charges on the interface of the silicon dioxide and the semiconductor called surface states or surface traps. I have to undo those as well. But those are small quantities. So the big quantities is the flat band voltage, the Fermi potential you have to come over, and the implant you add to uh, basically engineer the VT. So for example, I think uh, um, Puneet has been mentioning about standard cells which are high VT, low VT, um, and medium VT and so on. So high VT would be like in a 0.18, maybe close to 1 volt. Low VT might be 0.2 volts, or this might be 0.6 volts, something like that. So depending on your requirement, if you want really, really low power, you want to go for this. If you want a really high speed, you want to go for this. If you're somewhere in between, you go for this. So depending on your requirements, you can choose what kind of VT devices you want. So the technology which you're choosing, typically they will provide you these VTs. Sometimes they might just provide you just two. So I think we'll stop here. There is another element to the VT, which is the bulk control, but I think we'll do that in the next class. But is everyone clear about the different components of the threshold voltage? Also, I want to mention that, okay, so what are these things dependent on? Like, as I said, this is intrinsic to the process, and all these are dependent on temperature as well. So as the temperature increases, actually this entire quantity decreases. The VTN decreases. This is the part which is engineered. The designer has only control by controlling this bulk voltage, but that we'll talk about it in the next class. But this part, this is already built in into your device. So when you choose a technology, you just get this, and then with temperature this will vary, but you can't change the VT. It'll vary with process, what's called process, because they have different corners, because they can't really control this very accurately. So even this quantity varies quite a bit from part to part to part, and then varies over temperature as well. But detailed mechanism of how it varies to the temperature, again, that's something it'll take some time because there are a lot of conflicting things. Like for example, in VTN, there are parts which are increasing. The flat band voltage might increase, QV might decrease, FF might increase, and the resultant it's a decreasing part. So that may be when we do like maybe one advanced MOS class, we can cover all that during that time. But this is sort of the basic mechanism of how you control the channel by controlling the gate voltage or the plate of one side of the MOS device. So I think I'll stop here, but I want to take questions now and see if anyone has questions on any of the stuff we've covered so far. Any questions on either the components or the functionality, how it's inverting, or anything? Puneet, if you want to add something, please go ahead and.
Sir?
Yeah.
Sir, why do we use poly in place of metal in that part?
Yeah, so good question. So the first devices are actually done with metal. This will be a little bit more clear when we do the fabrication process. So what happens is the source and drains are formed. So when we do the entire device, let me see if I can grab another. So when we do the entire device, the process is like this. So you have this what's called a substrate, right? Actually, the gate is formed. When you send your layout for mass, first the gate is actually formed, okay? So let's say you put metal here. And then what they do is they take your mass for what's called your diffusion, and then they do ion implantation. So ion implantation is done to do the source and drain. So they actually do this ion implantation by doing bombardment, high-speed ions. But these are, they're kind of in a very thin layer. So what they do is they heat it up, and that's called the annealing process. When they heat it up, these ions, they kind of spread. They spread, and that's what forms your source and drain. So this is your N plus, and this is your N plus region, and that's your gate. The reason it's done with the self-aligned is because if you did this as a separate process, it'll be very difficult to control this edge, because these are not accurate processes. They vary quite a bit. So once you do the gate, then when you do the ion bombardment, the gate actually stops the bombardment under the channel and just forms exactly at the edges, well, a little bit encroached here, but almost exactly at the edge here, okay? Now when they heat it, this heating temperature is very high. Most of the metal, if you put it, they'll melt away, okay? Polysilicon, poly's temperature, melting point is much, much, much higher. So what happens is with poly, because even though you have bombarded this actually anneals and becomes a good conductor. And then they do something called salicide, where they actually put a thin layer of metal on top of this after they do this annealing. So short answer, if you put a metal, it'll melt it because they do a heating process after that. Poly doesn't melt. That answer your question, Gautam?
Yes, sir.
Puneet, you want to add anything?
No, sir. So I think I mean this is the part even I'm not 100% sure like the process which you explained right now.
Oh, the melting part. I think that's how the first metal one. That's one of the reasons actually they did it, and also the work function. The flat band voltage also was higher. So but that time the devices were almost like what 5 volts, like the 5 micron technology, 5 volts. So if you had a VT of 2 volt, it was fine. So when they went to finer technology, I think that those were the two problems. I mean, maybe there are additional problems, but these are the two problems I remember.
Like no, logically it makes sense the way you have explained. So I don't have any comments on that.
Yeah. If we can look into it. I haven't looked into it for a long time.
Okay, so I have
So that's,
just one question. Like
yeah,
you have talked about this HVT, LVT, and RVT.
yeah.
So one of the way you have explained like the impurity, the which we
The
usually
implant,
add,
yeah,
the
yeah,
implant which we add here,
right.
and I think okay, so my understanding, like we can also control with the help of the COX. Like if we will increase the width, if we will change the thickness of uh, the
Yes,
poly
yes,
and this thing.
right, right. So thickness will control this, but usually we don't, we want this as thin as possible because that gives you the speed as well. So yeah, so if you decrease this, then this quantity will increase. But you can see in the last one, um, yeah, like you can see, this is a very small port. But also, where is the other part of the equation? Uh, Yeah, well, this one actually depends on the implant as well. So I'm not sure. Are we talking about this one, increasing the COX, or maybe I was thinking
Yeah,
maybe
so
you're talking about this one.
so I'm just talking about like in general the HVT and LVT.
Yeah,
Uh, that we can also change with the help of the CX, because in HVT it is high threshold voltage and but it is a uh, the less leaky also.
right.
HVT high threshold voltage and the less leakage, yes. And the LVT it is fast but it is a high leaky also. So the leakage which I understood, like that is between the poly and the through the channel. So the capacitance become leaky in a LVT and it's not in a HVT.
Actually, the leakage I was talking about drain to source, not the oxide actually. So what happens is if you let's say have a VT of 0.2 volts, then when it is zero, it's not never off completely. It is always leaking a little bit. But you're right. So I think maybe I didn't make it clear. So when I'm talking about controlling the VT, I'm fixing the VDD. Okay, so for a given, so for example, let's say, so there are two scalings, right? So let's say 0.8 0.18 micron technology. So if I take the what's called the LVT device, that will be 1.8 volt VDD, that's the max, and VT is equal to 0.6 volts, right? If I take a HVT, it can be a 3.3 volt VDD where the COX is changed and VTs can be like 1 volt, right? I think that's what you're talking about.
Sir, I'm not sure
Mm,
because
mm,
I'm not talking about this 3.3 volt. So my
mm,
understanding till now, my understanding was in even in the 1.8 volt,
Yeah.
we
exactly.
can
Yeah.
have a VT 0.6 and VT 1 volt by
Yes.
changing the
Yes.
COX.
No, no, but if you change the COX, then this will change.
Uh,
So,
okay,
so if you change the COX, then what will happen is if you increase the COX, then this will become 3.3 volt devices now. If you lower it, then this will become 1 volt
okay.
devices.
So that
So
I'm not sure.
yeah, so basically the scaling is done on two sides. So if you want, and the speed will change. So once you increase this, then your mu n over COX over 2, right? So this COX, if you decrease it, then your speed also changes.
Sir, one question.
Yeah.
Means from Punisher, you are saying that CX will change. That means for fabrication point of view, the thickness may be constant. So only you can change
No, no,
that
no, no. So
material.
Santanu, he's saying actually you change the TOX, which is right. And that's where you
Uh,
create this high voltage device, but then you lose the speed, right? Because your COX decreases.
yes.
Uh, So your VT will increase, but this will increase. So what I'm talking about is given a VDD, a same scale voltage. So that way my
Uh,
speed is constant, but then I'm changing the
yes.
VT. So I can change the VT to 1 volt, but that I have to do it through this implant.
Yes.
Did that make sense, Puneet?
Sir, yeah. So like I
So,
said, I'm not maybe my understanding maybe not correct till now.
like,
So my
but
understanding was like by changing the COX, I can change the VT, and I never take care and never thought about like it is going to change the VDD also. So I was like VDD is going to be same, and if I will just change the TOX or somehow if I will change the dielectric constant, I know that between the poly and the this that is again going to change the COX and that will change the VT.
yes,
So
you're right. It'll change it, but the problem is, first of all, I cannot have anything other than CiO2 because they just don't grow on silicon. The only reason they're using, the only thing I can use is silicon nitride, but those are only on GaN processes. So this one actually is fixed. I can't do much about it. TOX, yes, I can change, but once I change this, then my 0.13 micron device will become like 0.2. So for example, any technology I choose, usually I'm given two flavors of devices, right? The IO devices and the logic devices, right? So for example, if I choose the 90 nanometer, they will give me a logic devices, which is, I don't know, like I think 0.9 volt devices with VT of, I don't know, maybe 0.3 maybe, or 0.2 even. But they'll also give me another flavor, which will be the IO devices, which might be 1.8 volt or 3.3 volt devices. But these TOXs are larger now, but they are not as fast as this anymore. They are basically like 0.18 micron technology. So the VTs are different, but they are slower devices. They're used only for IOs. But for high speed, I still have to use this, where I can't change the TOX. The TOX is still whatever 60 angstrom or 40 angstrom, whatever that needs to be.
Okay. Thank you, sir.
Okay.
So one thing I can add here,
Yeah.
during I was in EST. So in that for standard cell design,
Yep.
where you were doing one cell, but
Mhm.
adding the layers VTLP or VTHP, it will create
And
other low VT or high VT transistors. Same,
and that
everything is same. Only we are adding some extra layers for low VT transistor and for high VT transistors.
and that's exactly what this one is for. So when you add that layer, so the N implant is tells you which implant they're going to use. They're going to use a dose of 10 to the power 12 or 10 to the power 11 or 10 to the power 10, depending on you want 0.6,
Yes,
0.2, or whatever.
that implant. Yes, yes,
Yeah.
yes.
So that's exactly what they do that for. So that one, you're keeping your VDD, the type of your device fixed.
Yes.
It's like a point. So in 28 nanometer, it will be whatever 0.3 volt or 0.5 volt
It's
device.
40 nanometer. Is
Yeah.
1 volt.
Yeah, 1 volt. But your VT will change with just this implant.
Yes.
But in that 28 nanometer, you probably have a 1.8 volt device too, but with a higher VT. But that one, the TOX will change. They will make it higher.
Okay.
I hope that made
Okay,
sense.
sir.
Yeah,
Yes, sir.
I think there's a
Sir, I have a
question.
question.
Yeah, just 1 second, Sadabdi. I think there's a question on the chat box. Somebody just sent. Okay, from Saurav. Sir, at oxide substrate interface, there always exists a positive charge due to some impurity. So what about that charge, or is there some voltage controlling that we can add to that threshold voltage equation? Yes. So that's this quantity I'm talking about, Saurav. So the question is at the interface, at this interface. Maybe go back to, yeah. So the question is, at this interface, there is always some charge here, some impurities, and some inside the oxide as well. What do we do about it? Well, that's this quantity here, which I showed you, in the last equation somewhere. Yeah, this quantity here. This quantity basically gives you, and it's a very small quantity. The impurity is very small, so it's a very small quantity. So if the charges are positive, you apply a negative voltage to get rid of it. If the charges are negative, then you apply a positive, another extra positive voltage to get over it. So for example, the positive charge was such that this required 0.1 volt. Then on top of the VTN you already have, this will add another 0.1 volt, but you can always change that by changing this implant. I hope that answered the question. Yeah, go ahead, Sadabdi. What's the question?
Sir, I was asking when temperature is increasing, then VTN is also decreasing. And if we see mobility will also decrease as they will collide with each other much.
No. So the VTN, yeah, the VTN
If
and the
mobility is decreasing, then ID will also decrease. But in case of voltage, if we see it is coming faster, if we are decreasing the voltage, VTN.
okay. So let me understand the question.
So
So
I don't.
are you asking if the mobility is as the temperature is increasing, is the mobility decreasing, and because of that VTN should decrease? Is that your point, or?
No, sir. No, sir. I was saying VTN and mobility both are decreasing when temperature is increasing.
Right.
So, if mobility is decreasing, then ID is also decreasing. And if
ID, yes.
if I'm considering VG, the gate voltage, if it is decreasing, then ID is increasing. So, how to know at a condition it is faster or it is slower?
Okay, so good question. So I mean, you kind of jumped ahead a little bit because you're talking about this equation now, right? So let me just bring this. So you're basically saying the ID equation, if I take the saturation current, it is mu n Cox over 2 VGS minus VT n square, let's say, right? And basically you're saying when the temperature increases, mu n decreases, and VTN decreases as well. So basically
Yes,
you're
sir.
saying this, in this case, the ID is decreasing. In this case, the ID is increasing. What's happening? Is the overall decreasing or increasing? Is that the question?
Yes, sir. Yes, sir.
Yeah, good question.
Yes,
So
sir.
the answer is the ID is actually decreasing. That's because the rate at which mu n falls is much higher than the rate at which VTN falls. Did that answer your question?
Yes, sir.
Okay. Yeah. So ID actually decreases with temperature. That's just a process phenomena. It's not done by design or anything. I mean, you can design it, but that's like device engineering. But typically in a
So
CMOS
that's
process,
why
that's
that's the
what you'll
reason
see.
we can't.
Go ahead. That's the reason why.
Sir, that's the reason we can't control VTN with respect to temperature.
You're asking, can we control VTN with temperature? The VTN varying with temperature is just a physical phenomena. That's a semiconductor phenomena, right? So what's the question?
Sir, I was saying you said VTN is inversely proportional to temperature, and the parameters of that VTN equation always
Right.
dependent to temperature. So that's the reason we can't control VTN with respect to temperature.
Yeah. So if I understand the question, you're asking VTN, all the parameters of VTN, like VFB plus the 2FF plus QB over Cox and Q times QDI. Let's say this is the implant over here. So basically, I think what you're saying is these are all temperature dependent, and the accumulation of which is as the temperature is increasing, VTN is decreasing. Yes, we cannot control it. We just live with it, and we make sure our circuit works for the range of temperature we are designing our chips. Like last time I said, for consumer, it's usually minus 20 to 85. For industrial automotive, it is minus 40 to 125. So we have to make sure our circuit functions within the spec for this wide range of temperatures. We can't control the VTN. We can't say for different temperature, I'll control the VTN and make it constant. We can't do that. You can control other parameters to make it constant. Like for example, you have a current going into some device and you want to make that constant with temperature. You can do that with circuit techniques, but you can't control the VTN because once that given from you from the from the foundry, that's just given. You can't do anything with it. I don't know if that was the question or something else. So, Satabdi, was that the question or?
Yes, sir. Yes, sir.
Okay. All right, good. Any other question?
Sir, I want to
Yeah,
poison
yeah.
again.
Well, go ahead.
So,
Good poison.
yeah, so guys, so you're talking about this VTN and temperature, and the temperature increases, then what is going to happen? So, like this, just one thing, just go back and just read. There is a concept of temperature inversion. So, there is a temperature after that, whatever the relationship you're talking about, that inverted. So, like right now, you're talking about increasing the temperature, mu n decreases, and then there will be one point when temperature increases and mu n increases. So I'm not going to discuss a lot about that particular part. So maybe you guys, what you can do, just Google it. What is the temperature inversion? And then just whatever we have discussed till now, all the semiconductor theory and the concept, apply that particular part and try to understand like why I'm talking about the temperature inversion, what happened after that temperature inversion point. And from the design point of view, frankly speaking, that's very important. So when we are going to discuss later on, then we will discuss like sir was just mentioned in one of the slide. There is the PVT corners, the design corners. So
Right.
in that sometime the temperature corner come into the picture, so maybe we will discuss that particular point, but I think you just
Yeah.
go and just explore it.
Yeah, and it's specifically valid in short channel, the shorter channel technologies now. In the longer channel, 181 nanometer, the inversion doesn't occur that much, but short channel, it's very important. But yeah, that's maybe we'll do like a short channel poison lecture one day, and we can cover that. I personally don't work in short channel at all, so I'm kind of like.
Yeah,
Almost stay out of those poison areas, but yeah, as a digital designer you'll be all working on, you know, 7 nanometer, 4 nanometer and all that, so you have to be aware of all this. um,
basically what happened, like I like the way you guys are asking questions, and
yeah,
I can
no,
see
great
like,
great questions. Yeah.
yeah, so you guys have a good understanding, or just developing a good understanding about the semiconductor part. And I'm sure like if you will just continue this particular part, it's going to be very strong, and you can explain any concept of VLSI with the help of these things. So
I mean, you know, just to kind of reiterate,
yeah,
the questions you're asking, I can guarantee, you know, Santanu, he's been in the academia for a long time. He can tell you, most MTech, even from good IITs, will not be able to even, you know, grasp this or even ask this question. So,
yes.
so you guys should feel very proud. And you know, people who are feeling like, oh, I'm not grasping it, you know, just sitting in the class, even understanding 10%, that's good enough. Like I said, I've been doing this for 22 years. I don't understand. Like, I don't know, maybe just 10% I understand. Even that seems far-fetched. So
Sometimes it
yeah,
looks to us like we are not grasping, but sir, what happened? Like, let us suppose whatever is going on right now here,
yeah,
and somehow, and after 1 year or maybe after
exactly.
6 months, someone just ask.
Right.
Then maybe your reply will be like, okay, at least you will say like, okay, yes, we have discussed something there, maybe something click in your mind. So in subconscious mind, you don't know what is happening. So don't think like if you are not able to understand fully here, but yes, like I said, 25% definitely you're understand, you're getting things, and the rest 75% is somewhere in your subconscious mind. Whenever you will just read second time, third time, uh, you will come to know everything.
I just, you know, 200% agree with that, and go back to that point which Puneet was making, and I always do. Don't take notes on the first lecture. Just
Yeah.
grasp all this, because all this will stay in your head. And you know, like he's saying, we'll be reading something um, somewhere, or hearing something, or reading a blog or something, and then you'll go click. Oh, this is why it was the mu n was changing. That's why I understand the what they were talking about, lattice vibration or whatever it is. So just like sit and soak the lectures, and the discussions. Actually, the discussions are even more important. So can I tell a short story, Puneet?
Yeah, sir. Yes,
So
definitely.
talking about like just soak it in, I'll tell you a personal story. So I must have been like When did I do that? So I was I think I was 10 years old. So I was building an amplifier for my father. I convinced my father, give me some money, I'll build an amplifier for our home. So I was building an amplifier. Obviously I didn't understand electronics that much. I just like looked at the circuit, just soldered them, this and that, made my box and all that. I actually created the speaker and everything. And the day when I want to test it, um, and this was in Cuttack where I'm in right now. So when I tested, I just couldn't control the volume. So as I was changing the volume a little bit, it would just like explode and then it'll go down slowly. So I didn't understand. So I used to always go for my help to there was a VCR shop guy who I have a lot of respect now, because the guy was a high school dropout but knew about electronics, everything. So his name was Nali. I went to him and I said, hey, I'm doing this and I get this explosion in the sound. And he immediately goes, oh, yeah, you have a linear potentiometer. Your ear hears in logarithm. And
Okay.
that's why you have, your sounds are increasing in log scale. That's why this is happening. I did not understand. I said, okay, whatever, give me a log pot. So he gave me a log potentiometer. I changed it and beautiful. Then it just changed very linearly. The sound was beautiful. 15 years after that, I was sitting in a signal processing class in Richmond, and they were talking about the log linear scale. And that's when it just went like, oh, that's what you're saying. Why I need to match it. So just to, reiterate, so it took me 50, so it remained in my head for like 15 or even whatever, almost 50, 12 years, I guess, 12 for some years like that. And one day it just went like, oh, okay, I'm trying to match the log linearity of my ear with this potentiometer. That's what was happening. So like Puneet was saying, just soak it in. You never know. Even if you take 10% of this, that's a lot. I mean, you guys, second year guys, you just can't complain. Just getting the opportunity to just being sitting here and doing just whatever you're doing great. You don't have to complain that I'm not understanding the concept, or it's going slow or anything like that. And don't worry about the grades and all that. Just follow the class, you'll be fine. All right, that's all I have. Puneet, you want to add anything?
No,
Any
no, nothing, sir.
question?
Nothing, sir. Nothing from my side for today.
Okay, I think we have done enough today. All right, guys, thanks a lot. And
Thank
I
you.
just disturbed the.
Thank you, sir.
Thanks a
Thank you,
lot, sir.
Puneet. Thank
Thank
you.
Thank you,
Thank you,
sir.
everyone. Okay, thank you,
Thank you, sir.
everyone. Bye
you.
bye.
Thank you, sir.
Yeah, thank you, everyone.
Thank
Thank you,
you.
sir.
Bye.